So the object itself likely is more massive than the Earth, probably a little bit less massive than Neptune. Unlike the orbits of the known planets, is not nearly circular and planar. Instead, it is exceptionally wide, 20 times bigger than the orbit of Neptune.
For years, astronomers have speculated about the existence of a mysterious planet, Planet 9, lurking in the far reaches of our solar system. It's thought to be responsible for the unusual orbits of distant icy bodies, but the direct evidence? Still missing. Now, a groundbreaking study from Rice University and the Planetary Science Institute might finally shift the conversation. After running thousands of advanced simulations of planetary systems, researchers found something striking. In systems like ours, there's up to a 40% chance that a massive planet could be pushed into a stable, distant orbit, just like the one proposed for Planet 9. The central question they asked: could a wide-orbit planet, similar to Planet 9, form as a natural outcome of planetary evolution? To find out, they modeled thousands of different planetary systems. Some were familiar, like ours, while others included binary stars, extra gas giants, or multiple ice worlds. They placed these systems into star clusters, environments that mimic where most stars, including our Sun, are born. One pattern stood out. During the early chaotic stages of planet formation, gas giants often interacted gravitationally, leading to dramatic orbital changes. Some were flung outward. While many were lost to interstellar space, a surprising number were captured into wide, stable orbits, held in place by the passing gravity of nearby stars during those early chaotic years. In systems resembling our own, high metallicity, large gas giants, about 40% of the simulations created a distant planet that remained gravitationally bound, sometimes hundreds of astronomical units from the star. And the orbits these simulated planets landed in? They matched predictions for Planet 9, long, eccentric, and far-flung. By the way, if you're into cutting-edge space science and want more stories like this, hit the subscribe button. It really helps us keep exploring the edges of the known universe with you. What's truly exciting here is that the formation of a Planet 9-type object doesn't require exotic conditions. No need for a massive disk stretching far from the Sun. Instead, it can form closer in, then get kicked outward during early planetary interactions, what lead author Andre Isidoro calls cosmic pinball. There's another mystery this may help solve: the missing super-Earth. These planets, larger than Earth but smaller than Neptune, are common in exoplanet systems. Yet, our solar system has none. If Planet 9 exists, it would land right in that mass range, finally giving us our own super-Earth and filling a long-standing gap in our planetary structure. And what about the curious behavior of distant trans-Neptunian objects like Sedna? Their unusual clustered orbits have baffled scientists for years. The gravitational influence of a distant, massive planet could explain that, which is exactly what Planet 9 was originally proposed to do. This study shows that Planet 9's potential isn't just plausible, it's a statistically significant outcome of solar system evolution in clustered stellar environments. Traditional planet formation theories typically limit planet growth to regions within 100 AU of the star. But this new two-step model, gravitational scattering followed by stellar flyby stabilization, changes the game. It helps explain not just Planet 9 candidates, but also wide-orbit exoplanets we've already spotted in other systems. And there's more. This research may also help us understand rogue planets, planetary bodies that wander the galaxy untethered to any star. Most planets flung out during these early interactions become cosmic drifters, potentially explaining the growing number of free-floating planets discovered through microlensing and infrared surveys. So instead of being an oddball, Planet 9 might be a natural outcome of how planetary systems evolve in dense, star-forming nurseries. Still, Planet 9 remains elusive, and that's mainly because of how far and faint it is. Orbiting hundreds of AU from the Sun, it reflects very little sunlight and moves incredibly slowly, just a tiny shift over decades. Previous surveys like WISE and Pan-STARRS have scanned parts of the sky and ruled out some regions, but large gaps remain unexplored. That's where the Vera C. Rubin Observatory comes in. Scheduled to start operations soon, Rubin is designed to repeatedly scan wide swaths of sky with unprecedented sensitivity, the perfect tool to spot faint, slow-moving objects like Planet 9. If the planet falls within predicted ranges, Rubin might detect it within a few years. If not, it will still help refine the search and improve our models. Our solar system might be more dynamic and more typical than we thought. Planetary systems, even our own, may evolve through violent gravitational interactions, planetary close calls, and external stellar influences, not just slow and steady migrations. While we still haven't directly seen Planet 9, the growing evidence from simulations and orbital clues keeps the theory very much alive. With tools like Rubin Observatory coming online soon, the hunt is just beginning, and we may be closer than ever to finally catching a glimpse. Thanks for watching, and if you haven't already, make sure to subscribe for more cosmic discoveries, mysteries, and science news that'll keep you looking up.